This is lab group 6B and this is lab 7 MTF measurement of a diffraction limited system. We all shared equal roles in alignment and data processing. I'm Ridley and I helped with the schematics in the video.
I'm Cameron and I did the Zemax analysis. The objective of this lab was to measure the modulation transfer function of diffraction limited optical systems. The part list that we used in lab is listed below.
We started by observing the diffraction pattern from a collimated source. With an iris after the collimation lens closed down to its smallest size, we moved the microscope along the rail and observed the diffraction from the circular aperture. We found the +1 wave of defocus position further from the iris where we started to see a dark spot in the center of the beam, and we observed the -1 wave of defocus position closer to the iris. We can also calculate where these positions should be located using the formula given. As we scanned through the rail, we observed oscillations between bright and dark centers as we moved the microscope. We then inserted a 1 meter focal length test lens after the mirror, followed by an adjustable iris. We used the black dot method to find the best focus of the testing lens. The black dot method is when we translate the microscope along the rail until we are located at the +1 wave of defocus position and then back until we're at the -1 wave of defocus position, and the average of these two positions is the location of best focus. We found our average best focus to be 1014 millimeters, which makes sense since our test lens should be 1 meter long. We also observed the relationship between the aperture size and the distance between the + and -1 wave of defocus locations. As the aperture increases, the distance between the + and -1 waves becomes smaller in a linear trend.
A diffraction-limited optical system was created with a singlet lens and an iris aperture. The stop was placed behind the lens at 170 millimeters. Knowing the micrometer has a resolution about 10 microns and we needed to take at least 20 measurements across the area disc, we found the diameter of the area disc to be 200 microns. This allowed us to determine the size of our aperture, which we found to be 7.72 millimeters. With the iris set to this size, the entrance pupil of the lens was now determined, and the cutoff frequency of the lens was then found to be 12.196 line pairs per millimeter, and the slit width was set to 82 microns. The slit was positioned at best focus using the same method used earlier in lab. From our calculations, we found the best focus to be at 1047.5 millimeters behind the lens, which was similar to the best focus positions found earlier in lab. The microscope was used to set the width of the slit to the inverse of the cutoff frequency, which in our case was 0.08 millimeters. To measure at -1 waves of defocus, we then moved the slit back to the position where we had found the -1 wave of defocus. The image on the left is us using the microscope to measure the slit width. The image on the right is a picture of our setup.
In this video, the slit is translated transverse to the optical axis, and with the chosen slit width of 0.08 millimeters, the power of the area disc is profiled so that we can measure the MTF. The line spread function at best focus is shown here, and it follows a nice Gaussian profile, which we expect from our Gaussian beam. Using the line spread function measured earlier, we were able to calculate the MTF, as shown here. In the MTF plot, at best focus position, the MTF results indicate that the MTF flow follows closely to the theoretical curve up until the cutoff frequency, which we calculate to be around 12.196 line pairs per millimeter. And while we expect the MTF to fall off at 0, in this case, it actually shoots up towards 1, which is not what's supposed to happen. So this is likely due to an error in our measurement or an error of us applying the code to our data set.
The figure shown is the plot generated from Zemax for our optical setup. It has a slighter grade of cutoff frequency around 14 line pairs per millimeters, but overall it follows a very similar trend to our MATLAB theoretical and measured MTF. The difference in line pairs per millimeters can be attributed to displacement in the slit and actual best focus.
Shown here is the line spread function for -1 wave of defocus. We expect to see a dip in the central peak because of the dark ring that's found in the defocus location, but the line spread here has a greater width than at best focus, which is what we expect. The beam was profiled a second time at -1 waves of defocus, and the same data processing technique was followed for this data set. So in here we show best focus and -1 wave of defocus, and we can see the different value but generally follow a similar behavior. And we see that in the defocus position, the MTF is lower in magnitude, which also expected, as images will be blurrier as the system is defocused. A big cause of error in these measurements is the coarse measurement of the slit location, as it was difficult to tell where the slit was located inside the housing with reference to the rail.